Physics students, good afternoon. Mr. Fugit here. In this video today, we're going to be looking at our understanding of collisions, as well as momentum and impulse. And we'll be applying what we've been learning in class to solve a problem involving a collision between two objects. Specifically in this problem, we're going to be looking at something that we call impulse, which is related to objects changing their momentum, as well as forces applied over a time period. So this problem, this video, is specifically geared towards problems 16 and 17, which are really a two-part problem at the end of homework assignment 11. So the problem statement reads as this. A 0.52 kilogram softball is pitched at a speed of 15 meters per second. The batter hits it back directly at the pitcher at a speed of 25 meters per second. The bat acts on the ball for 0.014 seconds. What is the magnitude of the impulse imparted by the bat to the ball? So here, we're looking at what we call an impulse. Okay? An impulse, which when we deal with equations is represented by a capital J. Okay? We've talked about impulse as a way of describing when an object's momentum is changed. Okay? So we've said impulse, J, is equal to an object's change in momentum. Okay? Oftentimes when objects collide, the momentum of one of those objects, or most of the time both of those objects, will change. Okay? And that change in momentum is referred to as what we call an impulse. Now, that impulse, or change in momentum, is also created by a force applied on that object, or really a force shared between those objects over time. So I know the problem statement sounds a little bit weird when you hear the phrase, the bat acts on the ball for 0.014 seconds. Really what that means is that the objects are in contact for that time, 0.014 seconds. And hopefully for me and my students, you can think back to the video that we watched in class where the laboratory tested the baseballs and bats. It's a very similar scenario to what's going on here. So what I would do is, again, as we do with any type of collision scenario, we want to draw a picture of what's going on. So let's say we have a bat here. Yeah. It's kind of the barrel of our bat, and then our handle down here at the bottom. And then we have a softball that is being pitched, coming in to the bat, moving one way, and then it is hit and comes off, traveling the other way. Now we're told some information about the softball. We're told it initially moves, it's pitched at a speed of 15 meters per second. So when that pitch is coming in, I'm going to say that my initial velocity is negative 15 meters per second because it's moving at this speed in the negative direction. I'm going to call this final velocity coming off the bat 25 meters per second. I'm going to say that's positive because we're now moving in what I would define as the positive direction. And we're told that our ball here has a mass of 0.52 kilograms. Now clearly, we can see that the momentum of the ball is changing. It has a negative velocity coming in, a positive velocity coming out. Since momentum is the product of mass and velocity, we know that the momentum of the ball is changing. Now, the first part of this question asks, what is the magnitude of the impulse imparted on the ball? So we're looking for this value in here. What is our impulse imparted by the bat on the ball? Now there's two ways we can look at impulse. One, as a change in momentum, a measurement of how much our momentum is changing. Or two, as a product of force applied over time. Now we have to make a decision on what information we have to help us solve this problem. And here, we're not really told much about a force. We do know a time value, but we don't know force, so we're probably going to want to go with the change in momentum approach because we know our mass as well as our starting and ending velocities. So, as we looked at in class, I'm going to say that my delta P, my change in momentum, is my momentum final, P1, minus my momentum initial. I'm finding the difference from where I end compared to where I start. So delta P is equal to, well, P1, that's my final momentum. I'm going to do that in blue as I grab the red marker. M1, V1, and then I'm going to subtract that by my initial momentum. And I'll do that in green. I'll call that M naught, V naught. Now, we're not told anything about the mass of our ball changing here, so I'm going to erase these subscripts from the mass, because our mass here really doesn't change. Oop, I got my vector notation there. Okay, so now all I'm going to do is plug in what I know about the mass of my objects as well as their velocity. And again, pay close attention to the direction of our velocity. Direction matters a great deal when we deal with momentum. So delta P, our change in momentum, is equal to the mass of our ball, which is 0.52 kilograms, times our final velocity, which we're told was 25 meters per second, and we'll say that's in the positive direction, coming off our bat, minus, well, the mass of our object, which isn't changing, 0.52 kilograms, times our initial velocity, which we said was negative 15 meters per second, because it describes the pitch coming in. Okay, so we have all of our numbers here. Now we're going to mathematically solve our equation. I'll start by taking my first values, 0.52 times 25, so delta P is equal to, well, the product of these two numbers gives me 13 kilogram meters per second, minus 0.52 times negative 15 gives me negative 7.8 kilogram meters per second. Now here I have a positive value, right, for my momentum going to the right, minus a negative value for my momentum going to the left. So a positive, right, minus a negative is the same as adding those values together. So when I do that, my delta P is 13 plus 7.8, which is right at 20.8 kilogram meters per second. And that is a description of how much our momentum is changing in our system. Now, the question asks us actually for what is the impulse imparted by the bat to the ball. And now we've said an impulse is actually equivalent to a change in momentum. So this value, 20.8, is in fact our impulse. And we'll need this value to make sure that we can go forward and solve the next part of our problem, which is problem 17. Okay? So hopefully this gets us started looking at what we would call the impulse or change in momentum of a collision. Now we're just going to go right into solving the next part of this problem. And so here, we turn over to the next page. It's asking what is the magnitude of the average force exerted by the bat on the ball. So we're going to take this number, 20.8 kilogram meters per second. So our impulse, J, is equal to 20.8 kilogram meters per second. And we've also defined impulse, kind of the second approach we talked about, was an average force applied over time. Now we're told in our problem statement what our collision time is. It sounds a little bit strange. It says the bat acts on the ball for 0.014 seconds. That just means they're in contact for that amount of time. So I'm going to plug in what I know. My impulse is 20.8 kilogram meters per second. That's equal to my average force times our contact time, which here is 0.014 seconds. Now mathematically, to get that average force value, I'm just going to divide by my contact, or what I like to call collision time, 0.014 seconds. This value will cancel out, and then we can find our average force. It is simply our impulse over time, so 20.8 divided by 0.014. And I get a value of right at 1,485.7. And this is a kilogram meter per second over second. So a kilogram meter per second squared, mass times acceleration, gives us a value of newtons, which is how we measure force. Again, another double check to make sure we're doing this correctly. So hopefully this gives us an idea about how to look at collision from the standpoint of what we call impulse, changing an object's momentum by applying a force over time. Again, hopefully this gets you going in the right direction for these last two problems on homework number 11. Good luck.